Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3.
Up there. It's already up there and open.
Just push the space bar when you say
I
go.
think so, yeah.
Sure.
Yeah.
You have some more testing? Testing. Is this good? Testing. Testing.
Why don't you come over here? Just go. We're good.
We're good? Okay. Well, good evening, everyone. My name is Neil Pandya. Thank you all very much for coming tonight. I would like to give you all a very warm welcome to the 23rd Cyber Spectrum Meetup. Tonight's event is a special edition of Cyber Spectrum held here at the Wireless Village at DEF CON 26 in Las Vegas. The event series serves as a forum for the exchange of knowledge and ideas related to software-defined radio and generally aims to get people involved and interested and excited about applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. Our first speaker will be Dr. Chris Fallon, who will give a talk titled Opportunities for Radio Enthusiasts and Heaters of the Ionosphere. HAARP is just another instrument, or is it? His talk will provide some background of passive and active ways to get involved with HAARP experiments and perhaps with other natural ionospheric events based on prior and ongoing work. Dr. Fallon is an assistant research professor in Space and Physics Aeronomy Group at the University of Alaska Fairbanks Geophysical Institute. He is a computational and experimental physicist with broad interests in diverse topics including space plasma physics, high-performance computing, and information science. Our second speaker will be Michelle Thompson, who will give a talk titled Open Research Institute and Phase 4 Ground. One of the Open Research Institute's projects is called Phase 4 Ground. Their mission is to provide an open source implementation of DVB-S2 and DVB-S2X for both satellite and terrestrial amateur radio use. Phase 4 ground system has a 5 gigahertz uplink and a 10 gigahertz downlink. They are developing SDR software that heavily leverages IP multicast and RTP protocols to set up and tear down distributed remote radio functions. The radio reference designs are in GNU Radio, and she will provide recipes for many SDRs as possible. Michelle is active in Phase 4 ground community and in the GNU Radio community. Our third speaker will be Lucas Tesk, who will talk about SegDSP, which is a web segment digital signal processor that is tuned for connecting into a SPI server and to automatically demodulation and recording and parsing of RF data. This talk will be about what it does today, how was the development, how it works, and how will it work in the future, and what are the uses for it. Tired of losing the pass of an LEO satellite? Want to hear the recording from last week? SegDSP is an open source tool made in Go for learning and monitoring SATCOM and terrestrial comm. Lucas is a physics student at the University of Sao Paulo in Brazil and an electronics technician. He works on the website Let's Hack It and has an interest in such areas as computer science, programming, electronics, physics, and RF. He currently does research in SDR and reverse engineering of RF protocols. Our fourth speaker will be Luigi Freitas, who will give a talk titled Reverse Engineering X-band Satellites Data Link and the Worst Software-Defined Radio Ever. This talk will be about the reverse engineering process of the next generation X-band data link signal on board of sun synchronous satellites like Suomi and NOAA-20. From the raw IQ data recording to the decompressed high-resolution Earth pictures. This is the latest addition to the Open Satellite Project, a nonprofit organization that is committed to develop and publish software tools and hardware projects that enable the open source community to access spacecraft's non-sensitive data. The other half of his talk will be about the worst SDR ever that is made entirely of dirty and cheap parts. This project is intended to demonstrate how a software-defined radio works utilizing real hardware and comprehensive modular software. Luigi is a Brazilian computer science student developing projects utilizing SDR, microcontrollers, and FPGA, primarily for SATCOM and DSP applications. He also develops avionics modules for high-performance model rockets for university student competitions. Our fourth speaker will be Gavin Rossi. His talk will cover experience working with RTL SDR platform and implementing several SDR programs, including Luke Bernt's trunk recorder and Dylan Reinhold's trunk player Django app on the front end. They have been able to set up multiple receiving sites and cover both a countrywide analog trunk system as well as multiple digital P25 Phase 2 digital trunking systems, which make the SDR approach to police scanning really shine. One thing that sets apart this project from traditional police scanners is that using a trunk recorder as their backend allows them to time shift transmissions when multiple talk groups are active on each system, which is a big advantage over the limitations of traditional hardware-based scanners. He has archived nearly 40 gigabytes of radio transmissions. Gavin is an independent journalist and web developer who has created several local news websites and has done investigative journalism in New Jersey. He currently attends Stockton University. All meetup presentations will be recorded and posted online as well as streamed on YouTube. The videos for all previous CyberSpectrum events have already been posted. We have set up a channel on IRC on Freenode called #CyberSpectrum as a way for people remotely watching the live stream to contact the local group here with any comments or questions, as well as to alert us to any audiovisual problems. If you are interested in speaking at a future event or would like to present something, please get in touch with us. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would also like to thank Zero Chaos and the entire Wireless Village team for hosting this event. And with that, we will now get started.
All right, I'm just in touch with Chris, who's going to be joining us remotely, but while we get the Hangout set up for that, I'd like to invite Michelle to present. Round of applause for Michelle Thompson, please.
All right, open.
You're going to be doing the clicking.
He is.
Oh, you're clicking.
He's
Beg your
clicking.
pardon. Great.
Yeah. Should I need a thing?
One's wired, so I don't know how far you'll be.
Oh, okay. I can use the wired one if you like. Okay. Up here, you mean? Oh, okay, got it. All right. CQ DEFCON, CQ DEFCON. This is NYZ, QRZ. QRZ? Any hams? Any hams? Any contesters? CQ DEFCON, CQ DEFCON, W5NYZ, QRZ. Ah, QST. Thank you. All right, that was a contact. All right, this is an amateur radio project, but amateur radio is not all we do in ORI, so that's what I'm going to talk about today. So who are we? What do we do? Why should you care? And all of those questions. Phase 4 Ground and Phase 4 Space are two projects from Open Research Institute. This is a nonprofit. We incorporated in California in March of 2018, so we're kind of new. The directors are myself, Bruce Perrins, an open source activist, and Ben Hilburn, the president of GNU Radio Foundation. Now, so we're a new corporation, but we're not new at what we do. And the reason why we made this nonprofit was to give a formal structure to the work that we're doing and that we care about. In addition to the communications projects that we're doing, we also are active in open cars. As you know, self-driving cars are kind of a big deal. And almost all that work is proprietary. So Open Cars is an effort to open it up and to make it a little more transparent. Another place we're active is Open Codecs. Closed codecs don't really help us, so that's another big area. What do we do? Well, we make happy little radios. Why should you care? Amateur radio has a surprisingly large amount of proprietary stuff going on in it. And what we would like to do is make broadband, microwave, digital systems that can be used on terrestrially and for space. Amateur radio has a space allocation, and we've been active for almost 50 years in space. We're fighting against a huge rising tide of commercial, military, industrial launches. Retaining our position in space is kind of a big deal, and in order to do that, we need to move to the microwave bands. Now, the proprietary side and fighting the open source battle is one part, but doing an open source broadband digital system, multiple access system, doing it open source, there's another big reason for that, and that has to do with ITAR and EAR. ITAR is the International Treaty on Arms Regulation, and EAR is Export Administrative Regulation. ITAR is controlled by the State Department. They control those rules. EAR is controlled by the Commerce Department. Communication satellites have been on these lists for a long time. And in order to comply with ITAR, you have to do things like only talk to US persons about your design. Now, this is kind of a drag, as you would imagine, in a volunteer open source or amateur radio context. One of our particular innovations was to kind of fight back against that assumption, because there's a very large exception, an exemption in ITAR and EAR, and that is for public domain and open source work. You have to dot all your I's and cross all your T's, but that's a big reason why we started Open Research Institute. So what are we doing about it? Well, we're going to liberate DVB-S2 and DVB-S2X for amateur radio use for terrestrial and space. Why? Well, these protocols are open. And these protocols, the DVB, the digital video broadcast, are the protocols that are most commonly used in the downlink for commercial satellites. They're really pretty good. Now, as you know, most protocol documents are good for putting you to sleep, and there's no exception here. You know, they are long and detailed, but they're exceptionally good, and they're very useful for amateur radio. Where's the SDR part come in? Well, check this out. For each presentation, there's one slide that you could reduce everything down to. And this is our one slide. On the bottom here is the energy per symbol divided by the noise power. That's a fancy way of doing signal to noise ratio. You have a signal, you divide it by your noise. If your signal is very, very weak compared to the noise, well, you have a pretty poor SNR. If your signal's booming or you don't have a lot of noise, then you have a great SNR. So way over here on the end, that's kind of troublesome SNR. That's a weak signal, lots of noise. And over here, this is where you have your booming signals. This black line here is actually sort of a physical limit. Up here on this axis is your bandwidth. Like how many bits can you cram through that channel? How much bandwidth can you get through your channel based on your SNR? That black line, that's called the Shannon limit, and that's as good as you can get. Out here, cannot happen. Under the line, that can happen. These lines, these little jiggy-jaggy things right here, those are the things your SDR is really, really good at figuring out. So you measure your SNR, and you go, how close to that line can I get with a particular set of modulations and codings? So a modulation is, well, what shape is that signal? How many bits can you send at once? A very simple modulation would be a 0 or a 1, and FSK or ASK or whatever. You have two choices, and you send them over the air. And if your SNR is really good, you can afford to maybe send 4 different levels. You'd be able to pick them out, all the way up to 1024. So a complex modulation allows you to send more bits at once, but you do have to spend more power. The other part of the deal is the forward error correction. That's the coding. So when you say mod-cod, modulation and coding, picking the right mod-cod pair is what SDRs are pretty good at. And these two sets, this is what DVB-S2 and S2X give you. You can see that there's a huge number. So as your channel changes, as it gets noisier, less noise, as you may have more power available to either the received or transmitted signal, then you pick a different mod-cod. In our particular implementation, we're going to support all of them. There's a lot of different pairs. We're starting out with a smaller number spread around for experiments. So what does our radio system look like? We have one big fat downlink. This is the DVB-S2 signal right here. This is at 10 gigahertz. It's a time division thing. It's a bunch of packets coming at you with all of the uplink signals. And these yellow things are all the uplink signals. The uplink is on 5 gigahertz, and you get your own frequency divided channel. So your radio will negotiate and figure it out. You're on the uplink, you're combined, multiplexed, and transmitted on the downlink. Okay, not everybody, hardly anybody, has a radio that works at 5 or 10 gigahertz. It's not something you go to ham radio outlet and buy. So the point of this particular part of the project is to allow legacy radio systems to participate. Your radio that transmits FM, an analog signal, is collected and then packaged and then sent to the uplink. It's an amateur radio access point. So more fun for SDR. If you can imagine a radio that recognizes a signal that is either P25 or FM, an regular ordinary HT, and being allowed to transmit through a pretty powerful satellite, that's a really big step forward for amateur radio. Okay, so here's some other things that we're doing. We have a lot of RTP multicast innovations. We have the SDR package in a repository that focuses on this. And what we're trying to do with multicast, with IP multicast, is to set up and tear down modules so that you can have a distributed radio. There's lots of work right now with a DVB correlator. A correlator lets you figure out where the frame edges are for the downlink. We have an open source low density parity check. That's the forward error correction that we're using, and it's cutting edge stuff. We have an implementation that we've written, but it's for a GPU, and we're in the process of transferring it to an FPGA. That's a huge deal. We have a dual band feed because 5 and 10 gigahertz. You don't want to have a separate dish for 5 and a separate dish for 5, separate dish for 10. You can do it that way if you want. That's like having monobanders on every HF band. If you notice, 5 and 10, though, they're related. The second harmonic is an issue. So the design of a dual band feed was challenging. But we did it, tested it, and published it. We have filters for 10, and we have 5 gigahertz amplifier work. We have demonstrations of the ARAP, where we collect a bunch of legacy signals, package them up into a TDMA frame, and send it. We're having a ton of fun, and we're buying every SDR dev board we can find. So what do we need? Well, plenty more. Our team welcomes you. And we welcome volunteers, and we're trying very hard to make this an accessible way to learn how to do all of this ModCOD stuff. You don't have to be an expert to join. You just have to be willing to accidentally become one along the way. The plans for the finished product? Well, we want to have a complete reference design in GNU Radio. Our current product is actually a hackable badge. We are at DEF CON after all. It's called the Trans-Ionospheric. 10 gigahertz filters are another product that we'd like to have separate from the radio. Dual band feeds, and lots of words. The documentation of the process is very important to us. This is our badge. It's going to be available in the vendor area at Hacker Warehouse, and all of the proceeds from this badge go to help the first dev board for the actual radio. And the badge will talk to the radio, and it will be like a peripheral, radio peripheral, to show you the health of your uplink, downlink, and the payload. What do these radios talk to? Well, a payload. Completing a payload and getting a launch and dealing with ITAR and all that stuff is a big, big deal. But this is targeted to serve an amateur radio payload in space. They'll talk to badges, and they'll talk to ground sats. That's a payload that happens to be on the ground, usually a high place like a mountaintop or a tower. And the radios will talk to each other. This is what the payload looks like for GEO, geosynchronous satellite. This big giant box here is what our current payload is going to go onto. It bolts onto the side. This is a pretty big GEO satellite, and ours is a little box that goes on the side. This is the original team that went and talked with the integrator about it. Very exciting, kind of neat. Now, that's a proprietary closed payload. It's being done by Virginia Tech. We decided, launches are risky. You never know what's going to happen. So we said, why don't we take our open source mindset, open source about the ground, and apply it, go ahead and apply it, and do a payload design of our own. So recently we kicked off a Phase 4 space. Now, where are we? Well, we're here at DEF CON today talking to you about the successes and the plans and the battles and all that. We're going to be at Goddard in August to talk to NASA and learn more at their interplanetary workshop. And our next big engineering event is going to be at GNU Radio Conference in September. And we have what we call a block party. It's going to be really fun. We have our own lab, all sorts of equipment, and we're going to hack our way through the entire week and make as many blocks as possible for DVB-S2 and S2X. There's tons of links. We're trying to publish absolutely everything that we're doing about the project and all of our experiences with all the different SDRs, and all of this will be provided. Thank you very much. Any questions? Yes, sir.
For the LDPC implementation, what type of FPGA are you targeting? What do you do from the GPU to FPGA?
The question is what kind of FPGA we're targeting. We've generally, when we move from the GPU to FPGA implementation for the forward error correction, it has to be a fairly large one for 10 megahertz bandwidth, which is what we're targeting, up to 10 megahertz. And we've decided to target Zynq from Xilinx. And so that's kind of our favorite. So anything above like a 7045, we think will work. And there may be some ways to make it more efficient to get it to be a smaller part size, but we're expecting 7045 and above. But Xilinx has been the choice so far, and our experiences with Xilinx have been very good. We also have Ultra 96 boards, which is the ultra scale from Xilinx, and that's looking like it. Any other questions? Thank you very much.
Thank you very much, Michelle. It's a very exciting project. So next we're going to move on to Chris. He's queued up over Hangout, so what I'm going to do is I'm going to call him over FaceTime and share his screen as well. Just give me 1 second.
How about now? I was muted on the face Hangouts.
Is it going out your HDMI? I checked that earlier when I noticed that. I'm going to add you to Skype just in case. Do you want to try calling me back on FaceTime?
I can try that.
This one too.
Testing. 1, 2.
Hey. All right. So that's Chris there joining us remotely. Now I have to get his slides up. All right, there we go. What's the hotkey to full screen? And Chris, can we get some audio from you?
Testing, testing. 1, 2, 3.
Good.
Testing,
right.
testing.
Okay, so we're just going to sit you in the corner here. Screen, that is. Oh, I can't actually make it smaller. That's about as small as we get. Alright, there we go. What am I missing? The live stream. Can you unmute your Hangouts?
Hangout should be unmuted. Are you getting audio through Hangouts?
Big round of applause for Chris.
Thank you. This is really unusual. I'm looking at a wall as I'm speaking, but that's okay. Half the time I'm talking to a wall. It is really great to be here at my first DEF CON, although it's not quite the first. 99.9% is fun here in Fairbanks, Alaska, as it would be in Las Vegas. I'm sure with all the hackers and gadgets and things. Actually, no, that'll probably be the first and only during this presentation. And when Balin got a hold of me, I panicked a little bit because I've been on travel for a month, and we've just finished up a HARP campaign, so I really didn't have any time to prepare for a rather specific and special and technical audience, and so I didn't commit to anything except for a preview of a talk, since it's really not that easy to get a lot of mileage out of the mind control jokes and other conspiracy theories involving HARP. But then I realized I'm speaking to radio nerds, and in particular, radio nerds that are open to participating in HARP experiments. So, in that sense, the mind control is already working. I don't have to do anything, and I can just focus on the fun radio stuff and how to get involved if you like radios or art. Not that those two groups are mutually exclusive. And so there's really a lot to talk about, and not a lot of time to talk about it. So I'll do my best here.
The
Yeah, I can see everybody. Beautiful audience. That's
Give him a wave.
all right. Hey, awesome. I guess what I'll talk about today is I just want to give a brief overview of HARP and also some similar facilities, and give some examples of what I'm calling dual use experiments, where I've been trying to bundle a broader outreach component to sort of the hard science experiments. We're trying to use all parts of the buffalo because funding dollars are relatively scarce. And then I want to really dive into the opportunities for hams and radio enthusiasts for getting involved with the project, and that can range anywhere from running your own experiments, which at HARP, which costs just a little bit of money, and there's a couple options to do that: pursuing the usual ionosphere modification experiments, or HARP is just it's a big radio, and not just a big radio, but really one of the most exquisite and flexible and capable radios. And so it's really a good platform in many ways for prototyping new techniques in radio. As far as observing goes, and just taking advantage of the HARP campaigns when they're actually running, we can't prohibit anybody from participating if they're in the region. And there's a couple of different opportunities. If you can participate locally, that would be in the Glen Allen or Gacona area where HARP is generally located. You can also participate at sort of a regional scale if you happen to be somewhere in Alaska or even the Canadian Yukon Territory, and then also fully, but pretty much mostly in North America. And then I hope to be able to give a sequel to this talk, possibly beyond, which would be there's a lot of radios that we've been using in space and radio science, specifically space science, ground-based space science, that I think are really ripe for rebuilding with modern equipment, SDRs and such. And so I'll just give a brief hint of that towards the end. Okay, so this is the HARP facility. This is a rather old picture, and it tells a bit of history. HARP, we like to call it an observatory or laboratory. It's not just a giant HF transmitter or ionosphere heater, as we often say. That's only one component of it, and sure, it can heat up the ionosphere several thousand degrees Kelvin, at least the electrons anyways. But unless you have a suite of really sensitive instruments, who cares? It really doesn't do anything. It doesn't create earthquakes. It doesn't control mines. It doesn't do any of the things that a lot of people accuse it of doing. And it really takes sensitive instruments to actually to do science with it. Otherwise, we're just burning up 600 to 800 gallons of diesel an hour. And so the HARP facility itself consists, moving from left to right, we have the operations center, which was, that building was originally built to house the power plant of Over the Horizon radar facility in Alaska that was never built. The 445 megahertz radar array called MUIR, I'll talk more about that later. It's currently inoperable. Needs a couple $1 million of little maintenance work. And then, of course, we have the giant phased array, HF phased array antenna of HARP itself, the 40 acres right there, about 1,000 feet per side. Originally, the prototype was only about 960 kilowatts, and it was built out to full power, 3,600 kilowatts in 2007. And then in 2014, the Air Force announced that they were finished with the program, and they basically mothballed the facility and took out all the vacuum tubes and the transmitters. And they're very large vacuum tubes. I mean, they're as big as your leg. And so the university, when we were handed the facility or we took it over, we've basically been rebuilding the HARP array, reinstalling the vacuum tubes and recalibrating. And as of February 2017, we had a portion of it. We were up to about 2,000 kilowatts, and in September 2017, we were up to about 2,880 kilowatts. And then we have a bit of a mishap that we're working through right now. Our last campaign was at just under 2,000 kilowatts, and I'll speak about that in a moment as well. Other instruments that are at the site, we've got a Lowell DPS-4D Digisonde. there in the kind of the middle right. We have a really awesome HF receiving antenna off on the far right there, kind of a broadband HF receiving antenna, which is great. People can hook up their receivers to that really magnificent antenna. Then moving down the pad to the north there, we have GPS. And why do you need GPS? We already know where HARP is. Well, as many of you probably already know, GPS systems can be used for really sensitive measurements of total electron content along slant paths to the GPS satellite passing nearby. And one of the things that HARP can do is it can change the plasma density of the ionosphere directly overhead. Either increase it, sometimes decrease it in others, and so we can use GPS as a diagnostic for those sorts of effects. And then in the far bottom right-hand corner, that's where we have our optics for artificial aurora experiments, rheometers, which are like ionosphere opacity meters to the HF band, and our magnetometers as well. And so detect very minute changes in a region of space directly overhead. And when I say space, I really mean it in the literal George Clooney and Sandra Bullock astronaut sense of the word space. That's the region of the atmosphere that we're talking about. Basically, there's nothing there. There's just a little. So here's an overhead view of the array, and the dashed, the solid, the darker dashed line kind of on the right, February 2017, that was our first run by the university. The solid line to the right, that's where we're at nominally right now. We're at about 80% net power, 2,900 kilowatts. That doesn't quite tell the full story though, because as you probably know, the gain of this phased array antenna system really depends on its size. So we are operating both at reduced power, but also reduced gain as well. But still, as a 12 by 12 array, it is still by far the most powerful ionosphere heater on the planet. And then the two bands at the top and bottom, that's where we were at for this most recent summer campaign. And so we hope to bring it back up to full power eventually, but right now we're sort of in a money conserving mode, and we're not reinstalling those vacuum tubes quite yet, but that is our eventual goal. As far as the capabilities of the system in every way except for power, we have everything that we had before. It's a very programmable system. It can transmit in CW or AM or FM modulations in very complicated ways. Our bandwidth for AM and FM is 200 kilohertz essentially, and if that's for transmit, can be defined by a wave file, so it's really quite easy, and we have other pre-programmed modes. It can be operated in O mode polarization or X mode polarization. Those are circular polarizations, and then also linear polarization, just operating half of those dipoles, but of course that cuts your power down in half. And just sort of a rule of thumb is that basically we can change states at about every 5 microseconds. And there's some caveats there, certain things like changing the size of the array, for example, or changing the transmit frequency beyond 100 kilohertz or so. We can't do that every 5 microseconds. We generally have to retune the array, and that's a process that takes about 30 seconds. And so we're on the process of rebuilding this the system, and like I said, we had some generator issues that prevented us from operating at our nominal 80% power during this last campaign, and we were just about to fix those generator issues pretty much this week. And then we ran into what we like to call Alaska problems, and that is basically we've had a lot of heavy rains recently, and right where the Gocana River crosses that road through Gacona, some trees fell on the power lines, and it's basically cut off the power to the entire community, the Copper River community up there with Gacona and Harp and all that. So our house power is completely gone. It'll be down for a couple days, and we just can't do very much work there. So this is actually fairly common in Alaska, not just power outages, but just dealing in a very, very remote, very large environment. And we have a very small team, you can count them on one hand, basically. So it takes us a while to work through some of these issues. And and just for reference, the HARP facility is about 11 miles east of Gakona there on the map. It'd be behind that photograph, which originally I wrote it as courtesy of HARP, but then I thought if this is going to be online, then that might be maybe the reins were courtesy of HARP. No, just the photograph is courtesy of HARP. There are other similar facilities in the world, dwindling number. The first one was Platteville, Colorado. And then we had a number of others. Arecibo, it's not just a telescope. It was originally built as an ionosphere radar. It had a heating facility as well that was wiped out by Hurricane Andrew. And then, of course, as we know, Arecibo and all of Puerto Rico was hit by Hurricane Maria, at which they're still recovering from. Arecibo made it. They're still working through some issues there. IceCat in Norway, they have some ionosphere radars as well as a heating facility. Good portion of their heating facility was destroyed by a storm, and they recovered that a few years later. High Pass, east of Fairbanks, out in Two Rivers, big dog mushing community, is built from spare parts from Platteville that has since been decommissioned. It was quite an auction day in Fairbanks when that equipment went up for sale. Spear in Norway, very small budget facility up on the Svalbard archipelago. That was just a short time type deal. So they built it, used it, and then dismantled it. We have HARP, of course, and Sura in Russia, a couple hours drive east of Moscow. And I've indicated sort of with the question marks, the facilities that are kind of in kind of shaky status in one form or another. IceCat, their radars will be fine, but we don't really know what's going to happen to the heating facilities. Arecibo as well, NSF has cut their budget from about 10 million a year to 2 million a year, and even 10 million was kind of a shoestring budget. So it'll be interesting to see what they do in the future. And HARP also, the Air Force divested itself of it. Now it's run by the University of Alaska Fairbanks, which is quite a small university in a rather small state in the sense of population-wise. And we're in a situation now where even though we have federal clients or users that pay for experiment time, even at $5,000 an hour, we're losing money with every hour, but we hope to make it up in volume. And that math actually does work out, but we're not selling enough time at the moment to make a profit. But actually, we're on an upward trajectory. But in the meantime, it's a weird situation to be a small university subsidizing federal experiments in a way. This is just a comparison. The aurora, it fills the whole sky, but the artificial aurora is not quite that spectacular. In fact, if you can see it with the unaided eye, it would appear only about the size of the full moon or your thumbnail held at arm's length. That's if you can see it at all, and there are very few reports of people actually seeing this, and when they do, it's right on the edge of visible threshold, so about as visible as say the Andromeda Galaxy. And so that's on the left, that's a picture of the HARP spot taken from HARP with one of our all-sky cameras, and that's in the 6300 or red line emission. That would be the red, deep red color of the aurora that we don't see all that often here in Fairbanks. Usually we see the 5577, which is green. And to create an artificial aurora, all you have to do is basically transmit O-mode polarization at a frequency less than the ionosphere critical frequency, straight up, although it tends to work better in the magnetic zenith direction. And I thought, well, hey, we can, instead of just transmitting CW, what if we modulate that transmission with an SSTV image? And sure enough, we got artificial aurora, and we transmitted SSTV image. So we got more bang for the transmitter dollar there, and that was great. Had a lot of fun with that. But I encourage, and I try to encourage people also that are in the area to try to take pictures of the artificial aurora. We've had some accidental photographs of the artificial aurora. They didn't know HARP was operating, and they're trying to take pictures of the sky. for whatever reason, and they just get this annoying little spot that turned on and turned off in their images. And so this is actually capable with viewing this is capable with consumer grade equipment. We do have a big telescope, not a good-sized telescope on site. It was disassembled for us, courtesy of the Air Force, but we still have it. So if there's anybody interested in putting together a big telescope to take these really remarkable movies of the artificial aurora, it just sparkles and moves. It's just spectacular. Hey, we're willing to do that as well. One of these days we'll get around to it, but I know it's the wrong wavelength, but still, optics can be fun as well. And there's also reasons to, as radio scientists, to look at the optics as well. And I'll show a picture of that. And then finally, during the summer campaign, as I was approaching the end of my NSF grant and have to write some more to get some more HARP time, hey, why not whisper all over the continent and use the Whisper protocol, the WhisperNet, and everybody's listening. And so we have this great network. And why not try to do some actual radio science using basically citizen science reports, the automated Whisper network, to say vary the transmitter parameters, change the polarization, change the direction of the transmitter, change the frequency, et cetera, et cetera. There's really quite a few experiments that we can do. And this is just a diagram of the spots that we collected during the 3-day campaign, about 330 spots from about 98, I think, unique observers. And this can be important because HF propagation is still a hard problem. We really haven't made any progress on it, partially because we don't have a lot of data, but hey, here we have this, we have a pretty good network of observers. Maybe we can do something with this data and improve our computer models of HF propagation. And I think, I was pretty pleased with the results, and I hope other people were pleased in participating with it. This is just the statistics from the whispernet.org website, and it looks like on the 80 meter and 40 meter where we advertise that we were going to be operating during the campaign, we see some pretty big bumps, pretty significant bumps, I think, there on the number of spots collected on those days. Those aren't all reports of HARP itself, but I think my hypothesis is, and this remains to be tested, is that more people were listening, more people turned on their systems, and when they do that, just the total number of spots is going to go up. So I think this is a preliminary indication of success. So this is all well and fun. So now how, and these are sort of our like I said, our dual use experiments. And so if you want to get involved, how can you do that? Well, basically, at least in the science community at the university and community and the research labs, we have various principal investigators, PIs, and they typically receive grants, and part of those grants they spend on HARP time. And we have researchers from NSF, National Science Foundation, Air Force Research Lab, Office of Naval Research, and Department of Energy. And the current user fee is about $5,000 an hour, billed in 5-minute increments, and that's progress. We're billing in 1-hour increments, much worse than the phone company. There's been talks about increasing that up to 10,000 an hour, but we'll probably keep it at 5,000 as long as we can. And this includes basically the transmitter time itself, and also we'll set up the experiment for you as well, and provide some logistic support if you have instruments at the facility. And we have instruments not just at HARP, but Poker Flat Research Range, which is north of Fairbanks. It's the only university-owned and operated rocket range in the world. And at least optically, we can see HARP, and we can put radio receivers there as well. As a rocket range, they're a little bit more nervous about putting radio transmitters on the site, but receivers, just fine. And so if you have some money for some HARP time, and we do take Visa and MasterCard, and we did have one crowdfunded experiment by a resident in Fairbanks, KL4IU. Basically, if you have a little bit of money for some HARP time, you would join in on one of the Campaigns, we've been operating 2 campaigns per year. We're trying to bring that up to 3 campaigns per year. Generally late fall or very early spring, perhaps even winter. And for those 2, we usually want to have relatively dark conditions in the early evening so we can do our artificial aurora experiments. In the summer, of course, they're no good because we just don't have a large supply of darkness in Alaska. But then we do a summer campaign, and there are some interesting things to study in the summer, like why don't our experiments work in the summer? There's a lot of D-region absorption that happens in this region that I think is a rather unique compared to lower latitudes. If you happen to have a whole lot of money, cash in some Bitcoin or something, maybe in a couple years, and you can want to afford, 20 or so hours of HARP time, hey, you can have your own campaign. We might be able to drop that down to 15 hours or so. But yeah, around 20 hours, that's, you tell us when to run and we'll figure it out. And you can email me or the official address to talk about that. So here's a typical experiment campaign. Right now, they've been running about 20 hours. In April, we had a bumper crop, and we're running about 40 hours over multiple days. In July, this is sort of a mini campaign, as we called it. We wanted to test out some new techniques of operating the transmitter at lower cost. And in the fall, our next campaign, can't really say exactly when that will be. We're negotiating with Arecibo because we're looking for favorable lunar conditions for darkness. If the full moon is up, then that hurts our artificial aurora experiments. And Arecibo and HARP are competing for the same new moon. And so we're trying to coordinate a little bit so we don't have to make our users be in 2 places at once. And as radio enthusiasts, so maybe if HARP isn't necessarily your thing, or ionosphere heating, what we really offer, though, or we offer a number of things. One, radio spectrum in Alaska, if you want to get an experimental license or some license to use part of the radio spectrum, it's actually very easy in Alaska. This has been one of our underutilized assets or unrealized assets, is that just as a large empty space, it's really not that difficult to get radio spectrum. The requests are granted really pretty easily. We also offer space and support at the HARP site itself and at Poker Flat and the Geophysical Institute. And typically we have sort of a set for some types of usage, but really this is all negotiable from 0 to the standard rates. We want people to have their instruments here because, like I said before, HARP, the transmitter itself, is nothing without instruments to listen to it and observe the effects. And so it's in our interest to have as many instruments available. And so if you want to set up a remote ham station, I think we can do that with next to 0 cost, because that would be really a pretty cool thing. We offer, heated shelters, some logistical and technical support, power and internet and all those good things. Okay, so let's move on to, I guess, some of the experiments that when thinking about this talk, that I think are accessible to amateurs and particularly enthusiasts of software-defined radios. And one of those, I think the most accessible, if you're in the area, you have a radio nearby the facility, is stimulated electromagnetic emission experiments, or SEEs. And this is what happens. So we have a carrier wave from HARP, call it 4.2 megahertz. And what they found, what was discovered maybe years ago, about 10 years ago, let's call it, is that if you have a sensitive HF receiver, of course you hear that carrier wave loud and clear, even if you're in the ground wave shadow, so you're not listening to the HF ground wave. But of course you're hearing a really strong reflection, 3.6 megawatts of high gain. Sorry about that, it's probably a telemarketer. Of a high gain antenna, and that when that reflects, they'll go away. And so you'll hear that carrier wave loud and clear, but if you listen closely and look at a spectrum monitor of what you're getting back, you're going to see other things reflected, at frequencies offsetting that carrier frequency. And this has been determined to be indicative of several different plasma processes, stimulated Brillouin scattering, ion acoustic waves. Basically, that powerful carrier wave is causing various effects in the plasma, including waves and density irregularities. And so then that HF wave begins to scatter at different Doppler shifts and whatnot, and you can receive and measure these sorts of things. And so that RF space radio that is an instrument that I know for a fact that has been used in several SCE experiments before. They're usually set up at a local area not far from with turnstile or cross dipole HF antenna. It's usually portable. It's like setting up a cross badminton net. And so SCEs, it's a hot topic of research, and I think probably one of the most accessible ways to get involved. Next would be to more active approach and scatter radio waves off of the affected region. At first glance, this might be one of the most inaccessible ways to get involved with HAARP experiments. This is a photo of the Poker Flat Incoherent Scatter Radar, Pfizer, one of the AMISR classes of radars. And so it's a very large UHF radar with about 2 megawatts peak power, about a 10% duty cycle, very high gain at 440 megahertz or wherever it's at. It's about a 320 megawatt peak effective radiated power, and that aperture is about 700 square meters. And that we use that radar to view the natural ionosphere, basically measure the plasma density and temperature and velocity as a function of altitude. And again, we're basically scattering off of empty space, and we're technically scattering off of the electrons, or more specifically, density irregularities in the electron density from ion acoustic waves and Langmuir waves. But even then, what we're working with is not very much. If we want to measure what's happening in a 15-kilometer slab of ionosphere near the peak density, that radar cross-section is about 5 millionths of a square meter. Basically, the diameter of the object would be like a BB the size of a millimeter, perhaps. And the entire ionosphere, if you just wanted to get a bulk measurement of the entire ionosphere, then we're talking perhaps the size of a marble. And that's so looking at a, just a tiny little ball bearing or marble at a distance of several hundred kilometers. That's the class of problems that we're working with in incoherent scatter radar. However, an interesting thing happens when you turn on a facility like HAARP and you pump the ionosphere, as we might say, with O-mode transmissions. And what happens is that a region of the ionosphere with a very narrow, in a very narrow altitude slab becomes highly reflective to radio waves of various wavelengths. And you need a much smaller system to be able to see these see this region of enhanced reflectivity. And that region of enhanced reflectivity has a number of interesting theoretical reasons, and it could also be interesting for practical reasons as well. And so that mirror radar that I showed in the earlier slide at the HAARP facility, that's just 16 panels of that AMISR system. It was a development prototype for AMISR, and the first version of Muir was even half that size. It was only 8 panels, and with that radar, we were able to basically see, basically get returns during HF pumping that were 40 dB or more above the signal to noise ratio, just enormous reflections. And so that's, maybe, and this is all relatively, relatively old equipment. It's state of the art in some ways, but perhaps not in others. And so maybe we don't even need those 8 panels of mirror to do some interesting science. And so I think this is really another opportunity for, between local and regional participation, is to do what I would call artificial aurora scatter, just to abuse the artificial aurora term one more time, but to scatter off of the artificial aurora, sort of along the lines that we you can have auroral modes in ham communication, basically reflecting signals off of the aurora to get non-great circle path contacts. And so when you fire up this heater, just there are so many processes that go on, and some of those enhance the reflectivity of the ionosphere in various ways. And so this diagram is just an attempt to illustrate some of the many different types of things that are happening all at once. And this was, I believe this is probably, judging by the angle of those straight lines kind of moving to the upper right. Yeah, that's the, those are aligned with the magnetic field. A lot of the physics is aligned with the magnetic field. And these are probably almost certainly Arecibo experiments just by the slope of the magnetic field. At Alaska, it's nearly vertical. Arecibo, not quite so much. And so this is actually a plot from Arecibo itself of the typical electron number density as a function of altitude in the ionosphere, going from about 100 kilometers on up. The Arecibo ISR, that has an area of 73,000 square meters as opposed to just 700 square meters of Pfizer. Arecibo was originally designed as an ionosphere radar, and originally it was thought that the radio waves would scatter just off of the electrons that had a quite high thermal velocity, and so they're expecting a very significant Doppler spread in the scattered waves that would have to be received. So they thought that Arecibo would need to, or that any sort of ISR would have to have an enormous bandwidth to receive. And as you know, if you're receiving at a higher bandwidth, well, you're absorbing more, you're receiving more signal, but also more noise. And so that's why Arecibo was constructed to be as large as it was, is because, all right, well, we're going to get a lot of noise, so we need a huge dish to get the signal. It turned out probably should have done the test first, because it turns out the actual Doppler spread is determined by the ion acoustic wave velocity, which is much narrower than the electron thermal velocity. So you don't need a dish that big. But what we have now is the largest, most exquisite incoherent scatter radar in the world. That little spike, though, in that density profile, that is what's happening when they turn on the heater as they're measuring the density of the ionosphere. Plasma density is basically more or less a function of signal to noise ratio received by the radar. And so what you're seeing in that spike is a huge increase in signal. That's not number density of plasma, that's just enhanced reflectivity. And so that mirror radar is not nearly anywhere large enough to measure the natural ionosphere density. But when we get that huge spike in increase in signal strength, then that's what we're actually measuring, is just that little spike right there. It becomes highly reflective in UHF and VHF and even in HF bands. And what you get back is actually quite complicated. If you look at the spectrum of that signal, you get what we call the ion line or scatter that's surrounding the radar frequency itself. And then downshifted and upshifted from that, we have what's called the plasma line, and that's usually shifted by approximately the heater frequency. So if your radar is at 446 megahertz, for example, the pump is at 4 megahertz, your HF pump is at 4 megahertz, then you're going to receive plasma line echoes at 500 megahertz and 442 megahertz. So there's various ways of various mechanisms involved, and each of those are all, of course, caused by different physics: Langmuir waves, ion acoustic waves, and density irregularities. Okay, so it still sounds like it's a bit of a stretch for people with normal sized budgets of less than $20 million to build one of these radars. However, HF bands and even the VHF bands, if we're not talking about the scatter off of Langmuir waves and ion acoustic waves, but just what we call field aligned irregularities. These are irregularities in the number density of the plasma, and these irregularities tend to be aligned with the geomagnetic field. And so basically you get Bragg scattering if you're scattering more or less perpendicular to these things. And that's very useful in some ways. We use it these field-aligned irregularities occur in the natural ionosphere, and with our network of SuperDARN radars in the northern and southern hemisphere, we use those to generate maps of ion or plasma winds across the polar caps, as we see in the color image there. And that little red spot, those are field-aligned irregularities generated with HARP. Well, that article on the far right, that HARP amateur test successful article reporting on the work of Ed Kennedy and Ed Cole. Well, he just used ham equipment back in 1999, the early days of HARP, before it was even the big array. It doesn't take much to generate these field-aligned irregularities, actually. And with a 1 kilowatt VHF transmitter, okay, that is fairly significant for ham equipment, but certainly within the realm of our licenses. They were able to communicate basically by scattering off of these irregularities far over the horizon than you would otherwise be able to do with VHF. So here's a pretty unique ham mode or communication mode that can be done with ham equipment that I think would be, this is one of my next attempts, is to try to reestablish this type of scatter or communication sometime in the near future. Okay, and again, regionally, you can, if you are in the region, to be able to do these sorts of experiments, you can photograph the artificial aurora. There's that spot right there taken from north of the Arctic Circle. However, if you're interested in receiving satellite downlinks, area of research is scintillation. If the line of sight from your receiver to the satellite passes through that red spot there, or even the region above it along the magnetic field, you typically get a fairly significant amount of scintillation. And that is an interesting subject in and of itself and has wide interest, particularly among the synthetic aperture radar community and others. And so these two, so the optics and the radio can be combined, and the effects are related. This is a side view of the artificial aurora as a function of time. So we have altitude, time, and then the artificial aurora is the brightness. But then superimposed on that in the orange there is the HF enhanced ion line as measured with mirror. And so there is certainly some correlation between these two features, between the radio features that we're measuring with radar and with the optical features that we can measure with our low light cameras. Okay, so what about global participation? Well, I'm still working on this and I'm open to some ideas. And one of the things I can think about is validation of the models that we do have, such as VOACAP, the HF propagation model. You know, how good does it work? Does it work well for a point source in the Arctic pointing to the north or to the east or to the south? How does it work with various polarizations? And to do that, now we really have an opportunity to validate that model using our network of reverse beacons, such as WSPR. And there's a fair amount of interest on that. The map on the left basically shows the web traffic to one of the HARP websites during a campaign. And so this sort of indicates the receivers that we have. Of course, those people don't all have receivers. However, these are the people that are interested in HARP, and there's a significant overlap between HARP and radio enthusiasts. So that's the network that we have to work with. And it's also a way to develop perhaps new DX techniques in digital modes. If you have a 200 kilohertz, very flexible beam swinging antenna system, such as HARP, and we certainly have a fairly decent number of listeners that will report back. And so, and I'm open for suggestions for things to do in future campaigns, and as long as I have science experiments and funding, you know, I'll do my best to bundle these types of experiments with some of the hard science experiments, and then also to seek out and reserve certain amounts of funding for experiments that can invite a more broader participation. So always open for suggestions there. And then finally, moving on to the instruments that we use for ground-based space science, I think the two instruments that have a lot of high potential to be reinvented are the ionosonde and the rheometer. Of course, we could always have use for receivers at sort of unconventional wavelengths, ELF and VLF, because that's one of the things that HARP can do, is use the high latitude or auroral electrojet. We can modulate that to generate ELF or VLF, and sometimes even without the electrojet. And VLF are interesting to listen to in their own right. The Aurora certainly causes some interesting emissions. We could always use other receivers, broadband recorders. These are all instrument capabilities that we're trying to rebuild. But going back to the ionoson and rheometer, to the right there, that's a typical plot from an ionoson at HARP, the DPS-4D. Basically, you can think of it as a variable frequency HF radar aimed straight up, has about a 30-degree field of view. Directionality out of it, just a little. And basically, it's HF, and so it's more or less timing how long it takes each pulse at each frequency to reflect back, and it's also measuring the polarization and direction of that return signal. The ionosphere is birefringent, so even a linearly polarized HF wave will basically split into O mode and X mode components, and that's what we receive. And so this instrument is very valuable. It's not nearly as expensive as an incoherent scatter radar, and it still allows us to generate plots of ionosphere plasma density as a function of altitude, at least to the peak density layer. We can't really transmit HF above that, except in some strange situations. But this instrument is still relatively expensive. If you can think of the progress that we made in forecasting the weather, that was largely due to the fact that we were able to establish a very dense network of observing stations measuring barometric pressure and temperatures and all that. But the number of ionosons, while is increasing, there's still few and far between, partially because this instrument here, this DPS-4D, it's about $300,000, and it's only a 100-watt transmitter, basically. And so I think we can do better. The Canadians sell one called Caddy for about $100,000. We had a sequence of students working on an SDR version here in Alaska, various conferences like at CEDAR. There's reports of students working on ionoson-like devices. So I think this is one that really has high potential to be reinvented with equipment at much lower cost or much higher fidelity. The other instrument is the rheometer. It's basically an HF receiver, typically between 30 to 50 megahertz or so. And it's directional, pointed straight up. Those antennas in the bottom left-hand corner, that's the old HARP rheometer, is just basically 4 of those antennas right there. It's looking straight up. And what is it listening for? Well, it's just listening to noise. It's listening to galactic radio noise. And under quiet conditions, all things being equal, follows a very, very predictable diurnal curve. And when the noise goes down, when that receiver stops receiving noise, those are times when we have high absorption in the D region. So none of that galactic radio noise is making it down to the ground. And so when the noise goes down, we know absorption has gone up. And these rheometers are very sensitive instruments. They're looking at variations in the noise that's actually less than the noise level of the receiver itself. And it's a very interesting, I think it's a pretty interesting instrument, and so far is not, to my knowledge, has not yet been reinvented by somebody clever. And it's a relatively accessible in terms of cost. You know, that the old system probably could have been built for $10,000, and I think it could be done for a lot less money today. So that's where I would start if I was going to build a new instrument for a facility such as HARP, or just for your backyard. Not my backyard, though, because I live under power lines, and the condo association would not be happy with that. So in conclusion, I would say that HARP and these similar ionosphere and radio science laboratories like Arecibo, they're on rather shaky funding ground. The future is uncertain. The trajectory for building interest and getting experiments, I think, is going up, but it's still an uncertain funding environment. So in my opinion, it's important to capitalize on these opportunities while they exist. And HARP and Arecibo offer really, I think, unsurpassed and unique citizen science opportunities that we haven't really capitalized on in the previous few decades that we've been doing these types of experiments, partially because we haven't had to, and also because we haven't had the internet. It's been much more difficult to coordinate observations among a largely dispersed group of people. I think astronomy is probably the only field that I can think of where amateurs really have the potential to be on equal footing with the or sometimes even better footing than the professional scientists with expensive experiments. And so I guess finally, I would just say, please continue to be awesome, build and write cool stuff with these SDRs. Tune in to HARP and share your results and thoughts and questions, comments, and concerns. You can email me. A lot of people tweet at me, and that's fine. Email is a little bit easier for me to recall later, and we can see if I can help you locate your equipment or your instrument at facilities like HARP or Poker Flat, or even to conduct your own HARP experiments. So with that, I'll just say, please come to our open house if you have some frequent flyer miles to burn. August 25th, it's a Saturday. We open up the facility to come up, bring your radios, take pictures, bring your tinfoil hats, and all that fun stuff. It's in the middle of nowhere, but is one of the most spectacular and beautiful drives from either Anchorage or Fairbanks, whichever place you choose to fly into, or you can take the boat up to, you can do that way as well. So thank you very much.
Can you hear me, Chris?
I can hear you.
Great. Any questions for Chris from the audience? I've got a question. And by the way, if my calculations were correct, it's $417 for 5 minutes.
Oh, something like that. Yeah, about $100 a minute, maybe a little bit less. So yeah, 417. That sounds good.
I was wondering, what was the most maybe interesting or amazing maintenance challenge or story, if you had one? Spectacular, interesting failure. It sounds like
and if you would share one with us.
Oh, sure. So one of the big challenges that's in constructing a facility like this, I didn't talk too much about the generators. They're 5 20-cylinder diesel engines. We need 4 of them to operate the facility at full power, but it's not a constant load, and that's a really tricky thing to do. So a lot of the experiments are on, off with cadences of a couple minutes or so or less. And so that's an interesting thing to balance with an electrical system. Where does that energy go if the generators are running all out, for example? And so they spin up and spin down to account for variations of the load. Well, people that are doing VLF experiments, they're often trying to modulate the transmissions at or especially ELF, like at 4 hertz or something, not for mind control, just, that's the brainwave frequencies, but around 4, we're accused of mind control for operating around 4 hertz and stuff, but I guess it is in the millihertz range. It was generating physical resonances in the generators so that these humongous generators will begin to rock. And if they keep going, they would just like walk themselves right outside of the facility. And so that's an interesting thing we're not allowed to do for that. Other modes, we have to be a little bit careful, particularly with like split array experiments and certain types of experiments. These transmitters, they couple to each other just as any phased array system would. And sometimes they can couple in ways that I would call sparky. So things blow up and antennas will catch fire. And those shelters that you can see in that photo, those are giant tube amplifiers with giant inductors that the plates will move up and down as it tunes to different frequencies and variable capacitors, and those will also catch fire as well in certain situations. There's a lot of interesting, lots of potential for maintenance issues that come up, but I think the walking generators is probably one of the fun ones.
Any
Any other questions for Chris? Who might be going up for the open house?
Hey, can you hear me?
Yes, I can.
Okay, great. Listen, that was a great talk. Listen, the $100,000. What am I buying for that? Is that a week's worth of time, or since you pointed out that there would be assistance and help with experiment setup? What is that?
Oh man, if you had $100,000, that's like that's like half a campaign right there. What is how many hours is that? Like 20 hours or so? Yeah. Well, that gets you a whole campaign, and so that gets several days. We try to operate, on sequential days, and so that's basically programming the transmitter itself. That's coordinating with other instruments. So I'd be running the Ionosonde, and if I guarantee you that if you're running with $100,000 worth of time, there's going to be other people bringing their instruments, their radios, their HF radios and whatnot, because that's one of the great things is when other people are running their experiments, if you have an instrument, you're going to be looking at their experiments as well. That's really how we've learned a lot. And so you'd have that sort of access as well. We usually share data as much, but it certainly gets you the full support of programming the experiment, making sure it works, debugging it, and doing our best to run it when you want it to be run, so long as it conforms with the technical capability of the transmitter and within federal law as well. And we could probably throw in a free T-shirt at $100,000.
Yeah, I was going to ask what kind of additional perks get thrown in. Question from IRC from Chris. Two questions, it looks like. Oh, no, one question, sorry. The field-aligned irregularities occur at lower altitudes? Question mark. And then the other comment was being able to do high data rate, long-range comms up in VHF would be amazing.
That would be amazing. So yeah, first question about the altitude of the field-aligned irregularities. Well, we have E-region irregularities, E-region of the ionosphere. That's maybe from about 100 to 150 kilometers altitude. We know how to generate those. Dave Heisel out at Cornell University, he has an HF radar out of Kodiak, and that's actually what he looks at, are E-region irregularities. The F-region irregularities, starting at about 150 kilometers on up. Boy, that's how far do those go up? We're not entirely sure. It's certainly above the region where HAARP is doing its direct interaction. It's several hundred kilometers, I would guess, just off. And again, this is a guess, so don't quote me on it, but could easily be 800 to 1,000 kilometers altitude. And so it's, again, in a very limited region in terms of latitude, longitude spread, but along the field line, they quite a distance as well, and should be able to scatter off of that region. Although probably if you're interested in detecting scatter or using it as a way to bounce radio waves and go beyond over the horizon or non-great circle propagation, your best bet would probably be to aim at the peak density region of the ionosphere, which at HAARP during the daytime is usually around 225 kilometers altitude, maybe 250 sometimes really in unusual cases it's as low as 200 kilometers. So that's what I would do. As far as the capability for high bandwidth VHF communications, hey, that just hasn't been tried before, so that's a great experiment to do. One I would certainly be interested in. I just don't have stuff to do that, and it's certainly one I'd be interested in applying for funding to try, and yeah, maybe I will.
And one last question. I'm very curious about what frequency allocations are available for HAARP experiments, amateur bands within its range, and what else?
Oh shoot, that is a slide I meant to put in here. Is one of our frequency allocation, and so basically we get. I could tweet it after the the workplace monitor is my Twitter. I could find a way to put that online. Actually, yeah, I can do that. But basically, yeah, our frequency allocation, we have a base frequency allocation, which is regions between about 2.75 or 2.7 or even 2.65 megahertz up to 10 megahertz. And the ham bands are excluded from that, along with several other notches for aviation and maritime and emergency use. However, every campaign or periodically we apply for a special temporary authorization, and I think we're looking into making that permanent, and that does actually include the ham bands as well. And so that was a question actually by the ARRL folks about whether we had a license to be doing this whisper test in the ham bands. And the ham bands aren't something we use regularly because we want to play nice with the ham community. We don't want to antagonize anybody or disrupt anybody's use of the ham bands. But for very limited cases, when the science objectives call for it, in the example of this whisper test for one, there have been a few limited others. We will encroach in the ham bands, but it's always for a very short time, and we really do try not to do that too much. But it is a nice option to have.
All right, one big final round of applause for Chris. Thank you for joining us, Chris.
Thank you.
And we'll keep an eye on your Twitter for that additional information. Thanks again for joining us. See you next time.
Yeah, thank you.
Bye.
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 Now we're going to cross to Lucas. Yeah, we can hear you. Can you hear us? Okay, so you can see me now? Yep. Okay. You need to share your screen. Yeah, I'm sharing here now. Okay. Okay. Yep. How many of you know me? I'm one of the creators of Open Satellite Project, which Luigi would talk afterwards. And I will talk about SegDSP. It's a really new project I am doing, basically just for two reasons. One, from research for DSPs. I'm researching DSPs for a long time now, like in the Open Satellite Project and other things. And I'm talking about. I will talk about the future of RF monitoring. First, I want to thank everyone for being here. I'm thanking also the invitation. It was a bit less time, so I didn't have much time to prepare a very good presentation. So I hope you like it. So RF monitoring, it's listen and record RF traffic. Okay, so it can be audio, it can be like digital signal, or
or even the HARP signal that's sometimes is not like a digital signal or anything. Okay, so what's the problem of doing that? So the most common problems for monitoring something is the SDR spectrum. So you have a limited bandwidth, like for example, I have a Lime SDR that has like 64 megahertz of bandwidth that I can read by a time, and that requires a lot of computing power to parse it. We have the CPU usage. The CPU usage is depends on what you're listening. Like for example, if you're listening like the 40 meters ham band, you can probably listen everything without any issues. But if you are listening like, for example, Iridium or even the geo weather satellites like GUIs that has the GRB and things like that, that has a very large bandwidth, then you might have starting problems with the CPU usage. Another very common thing is disk utilization and organization. So if you record a lot of stuff, it's very easy to get like one hard disk filled up, or you can't find this stuff anymore. So this is also an issue. And also network usage. So for example, if you are streaming to anywhere, you want to see what's happening, or if your SDR is a remote location, you have a network issue as well. Okay, so CPU usage, it's when you have too much channels. So I have an example here. This is just a random receiving I got here in São Paulo. So this is basically all digital audio channels from a local FireCops. And this is just 14 channels. It's a lot of channels to demodulate. It's not a very high bandwidth. It's like 5 or 10 kilohertz. It's like P25 or similar radios. But it's a lot of channels to decode. So how we do the flow to get like from the IQ to the audio itself or anything else you want. This is probably like for almost everyone here, it's very straightforward. But we would just to show how this problem can be, how this can be a problem when you have too many channels. So basically, you have an IQ stream, your SDR receiving 6 megahertz or something like that. Then you need to frequency shift to make the signal you really want to the center of the spectrum, so it's easy to demodulate and decode. Then you low pass filter it and maybe decimate, so because you don't need the 6 megahertz. Your signal has like 10 megahertz or 10 kilohertz or 15 kilohertz. So you low pass and decimate, so you just have enough signal you want. Then you pass through a demodulator that can be like for P25, can be like a AFSK demodulation, or you can be an FM demodulation or AM or anything you want. Then you can send this output stream to a recorder or a watcher. Okay, a watcher is something like a process that can for setting patterns or just you seeing what's in that stream. So when you have multi-channel, you still have like one IQ, but you need to frequency shift every single of the channels you are receiving. Okay, then for every signal, for every channel that you shift, you need to do the low pass, you need to do the demodulator flow, and put through the watcher or a recording system. So here the things start getting a lot complicated, because here you already have like 14 independent DSPs that's consuming a lot of CPU. But then you have another problem. Maybe you don't want only to listen like the VHF amateur band. You want to get the UHF or the 2 meter bands or the 1.3 meters band. or the microwave or anything. You want to listen several bands that your SDR cannot listen to single one. So then you need to have multi-SDR. And then you have several IQs. Okay? So this problem starts getting really, really bad if you want to listen or monitor several channels in several different frequency bands. So that's escalated quickly. You see, there is a lot of channels, a lot of process running, and maybe you don't even have the bandwidth on your network to do that. So what you can do? Well, you can divide and conquer. Okay, so basically, let's split the problems and into pieces. The first one is IQ. So you need to retrieve this IQ from SDR, and then you need to frequency shift to every channel you want. Okay, there's a very simple solution for that. That's what SecDSP uses. That's Spice Server. I think most of you might know that. It supports LTR, SDR, and all the AirSpice. And the big advantage of Spice Server is because it can deliver you like 6 megahertz of FFT, like 20 frames per second, and provide you with an IQ for just what you want. So it basically does the frequency shifting part and somewhat the low pass and decimating if you want. Okay, so this first part can reduce two things. You can reduce the difficulty to receive several streams, and you can reduce the network usage because you don't need to stream now 3 megahertz or 6 megahertz of bandwidth from the remote SDR location to where you are receiving or processing the data. You can just select, like, for example, 14 10 kilohertz channels that will consume a lot less than one big 6 megahertz channels. Then you go to the filter plus the modulator part. Okay, so the filter can be an AirSpy, but you probably want to do your own filtering depending on which settings of the signal is. So if you have like a FM signal, you want like a specific bandwidth, or if you have like PSK receiving, you probably want an RRC filter. So you probably will have like the LPF inside the first stage, that's Spice Server, but you want like a different filter inside your demulator section. So we can do it that. The SecDSP does that part. So what SecDSP means? It's a segment digital signal processor. So it connects you to a Spice Server. It pre-selects the channels you want. Okay, and it's all event-driven. So, for example, one of events that you have is like a squelch on or off. Okay, so for example, if you don't have any signal, you probably don't want to do anything. You don't want your demodulator section to work because it doesn't make any sense. It's also self-contained. So if you wanted just a single application that can demodulate like a single channel, it's just a single app that connects to Spice Server and outputs the audio. And it can output through 3CP or WebSocket. So you can listen on web, or you can just receive and pipe to another software. So then you have the third part. That's the recording and watching. So basically, you want to do something with that data. Okay, you might want to pipe to another application like Multimon NG to decode APRS or any protocol of that, but you might want to record it so you can see afterwards. For example, if you have like a LEO weather satellite pass or an ISS pass or something like that, you are not available on the time to listen, you can record to see it later or watch remotely. So SecDSP also does that. Okay, so it currently has a record to disk, so you can record either the IQ or the demodulated output. It has a web UI that you can monitor the full FFT spectrum. So even if you are listening like just 10 kilohertz, you can watch the full 6 megahertz from AirSpy. It says the status of the recording, if the station, if the SecDSP is blocked for control. It has a feature for record on squelch off. So, for example, if you get like a stream, you have like a fixed channel, like in one amateur band, like makes some sendings periodically. You don't want to record like a continuous stream of nothing. So you probably can set the squelch. So when the squelch triggers off, so there is some audio or anything, it starts recording. When the squelch kicks in again, it stops recording. So it just records the pieces that has a significant audio or something else you want to hear. And for future, we want to integrate with Hadoop's block storage. I will explain this later why. And you have like event-driven script execute. So basically, you want to execute some script when squelch kicks in or squelch kicks off, because you want to decode something, you want to warn someone, you want the SecDSP to send an SMS saying, okay, I got a signal from the ISS or something like that. So this is the web UI from SecDSP. It's pretty simple, doesn't have much to see. It uses a relatively low bandwidth because it just sends the demodulated output. For instance, for now it's demodulating like a WFM audio, okay, from the local FM stations. It's using like 200 kilobytes per second. Then what we got so far? For the Mewtwo SDR examples, we can solve it with SPI-Server, okay? Because the SPI-Server, you can like put several instances of SPI-Server and can just connect SecDSP to any of them. Then you have multi-filter in the mod because you can put like several SecDSPs running and each one for each channel. Then Record Your Watch also works with SecDSP. So what's missing? Well, the CPU usage. The issue is, even with SecDSP, we are trying to make a very high performance demodulation, like you can run in any machine like a Raspberry Pi or something, but it still uses a lot of CPU because it has several things to process. So you can reach a limitation. For example, this is in my machine, like it's an i7. It's using like 100%, so it's a single core of my i7 running at, I think, 1.4 or 1.5 gigahertz. It's, of course, not only the demodulation part, it's the web UI, it's all the client handling and everything. It's a lot to do. It's like a single core. It's probably, if you run more than one instance, it can share memory, and some parts of the process can share, so it doesn't use like a sync core for every channel, but you can expect like at least half core for each channel. So you can say like 2 cores, 2 channels per core or something like that. So what's the solution? The thing is, the demodulation process doesn't differ much if you use an i7 or if you use a Raspberry Pi or if you use an Odroid board or everything. It basically uses the same amount of power. It depends more on the clock frequency than the CPU itself. So what's the solution? Multi-machine. So you want to put several machines to do the work, but what? You will like put a lot of several i7 machines or things like that? So no, the idea is to use cheap SBC computers, single board computers with Docker. So for example, I have this Odroid cluster. It's a prototype machine. It has 3 Odroid U3. It runs like it's a quad-core processor, 1.5 gigahertz. I don't recall exactly. It runs Linux. It's pretty cheap. The new version, the Odroid C2, it's much more powerful than that, and it's like $40 or something. There is also this Raspberry Pi cluster that I got the image from Boise University, PhD candidate. It's a Raspberry Pi cluster. The first time I saw this, I just said, what the fuck, for what he's doing with that? But then suddenly I think, well, that might have a very good use. because you have several cores there, and then you can list them like several channels. So how this will work? So you can have like several machines with several SPI server containers. A SPI server ideally connects to one single SDR, but you can get like several SPI server containers, each of one connecting to one's SDR. So for example, here I have a Core i5 NUC from Intel that has like two air SPIs and two RTR SDRs. So I have four instances of SPI servers running, and then I can have like 4 different bands that I can monitor. You can also put several machines for that. For example, you have several locations with several different antennas and optimize them like that. Then you can spawn several SEG DSP workers. For example, each SEG DSP workers works for one channel, one demodulation. So you can set like for WBFM or anything like that. Or you can set through narrowband FM or PSK or AFSK or anything you want. And you can spawn several of them. And maybe a single machine can process more than one channel. So for example, if you have like an Adroid C2 like I have, or Adroid U3, you probably have 4 cores that has a nice demodulation features. Then you might be able to demodulate like 8 or 10 narrowband signals. But then you have 30 signals. You can just split like in 3 machines and put every worker in the machines. And then suddenly you just have like 3 machines running 30 channels and probably consuming a lot less power, like from my i7 running the same 30 channels. And then if you want to record it, you need to store somewhere. So that's the idea of using either the Hados block storage from Ceph, or even another shared file system like NFS or maybe a DRBD cluster or something like that. Because you want to like or have like a redundancy, or you want to do like a network RAID so you can split up the space usage between several machines. Sometimes you are listing like high bandwidth signals, and maybe a rotating disk is not very performing for several of these channels, so you might want to split between several machines or several disks bandwidth. Okay, so this is possible here. So what's the advantages of that? Well, you can scale however you want. If you want a single machine that runs everything like I do for tests, you can do that. If you want like one machine per process and one machine per SDR and everything, you can do that. If you want to put all your processing nodes in the cloud, because you can like dynamically create and destroy machines in the cloud, you can like allocate how much space you want, or you can just put like in cold storage that's very very cheap to store. You can do that. Then you can, because of that, you can have specific machine roles. So you have a machine that gets the SDR stuff, you get a machine that has the processing stuff, and you can have a machine that does the storage stuff. So you can like make, for example, the Odroids probably don't have a lot of storage, but they have processing power. Then you can like have a network NAS, network area storage, which doesn't have a lot of processing power, but you can like put like four 10 terabytes disks, and so on. So you can optimize the usage for each part of the stack for getting the best hardware you can for the lowest cost as possible. And as a future feature, I want to be able to spawn, to create and destroy dynamically workers of SEG DSP. So for example, I can monitor like 10 megahertz of FFTX spectrum that in normal conditions shouldn't have any traffic, for example, a reserved band or things like that. But suddenly something appears that and you might want to record it because maybe it's an interference, maybe it's some illegal transmission or something else. So then ideally you should have like you can get the advantage of the event-driven stuff to do that. Or for example, like I put in the presentation for LEO satellites. So LEO weather satellites pass like every 1 hour, 1.5 hours or 2 hours, or depending on the altitude of the satellite. So you don't need to record the channel or have the demodulator running 24/7 just because the LEO satellite will pass like in 5 hours or 6 hours for 15 minutes. So ideally, what you should be able to is have a software that is tracking the satellite, and when it's in range of your station, you can just pops up a new instance of SegDSP and starts recording and demodulating, and maybe sending the data to another server with the images or the audio or anything else. Then why though? Why you should do that? Well, I'm not sure how much people here receive LEO satellites or here the ISS or anything, but they have very tricky times to receive. You have optimal times that usually it's the optimal time to receive the weather satellite or the ISS is like once per week that you have the perfect pass, and not always you are on your station to receive that. Maybe you are like a local authority that wants to monitor illegal traffic, or maybe you just want to learn how distributed systems work. And this is a very good place to start because it's each demodulating flow is independent from each other, and that's how it works in the cloud. Okay, so you might don't have good internet to stream to the cloud, so you can test there, but maybe you can buy like a few Androids or a few Raspberry Pis. For example, the Raspberry Pi Zero that costs like $5, and then use that for processing. You can buy like 10 of them, it will be $50, and you have a lot of processing power for the modulation. So in resume, SegDSP is Dockerized, so it's intended to run in Docker. It's made in Go, so you can run in Windows and Linux and macOS. It's a single contained application, so it doesn't have any external dependencies than besides what your operating system already has. So you can just like download a single executable and run that, or you can just get the source code and compile it by yourself. It has a file recorder, it has a FM demodulator, a web UI, and it's made in Golang, which makes very easy to understand the code. And surprisingly enough, the Go compiler optimizes a lot the traffic, the demodulation process. For example, in Open Satellite Project, I made a library called SetHelper that has a lot of DSP functions specifically for PSK demodulation and the GUIs receiving in general. And I did in C++ with a bit of assembly. And basically, the code I wrote in Go, I wrote from scratch, using the same core concepts from the SetHelper, and I got basically the same performance. And the advantage of that, it's the code is more readable, and it's very portable. I can compile for Raspberry Pi, I can compile for a PowerPC, I can compile to x86 and everything. And it finds the best way to do in each platform. So what's the future? What's the plans for the future for the SegDSP? So the first thing I want is Hados block storage. For those who don't know, the Hados block storage is from Ceph. Ceph is basically a distributed block system, distributed storage system. It's open source as well. You can like use for virtual machines to file storage, block storage, or object storage. So you have, for example, an S3 from the same S3 from AWS, from Amazon. You have a wrapper that's compatible with their SDK and the storage in Ceph. Hados block storage is one of the ways. So the idea is to put in Hadoop because Hadoop is really easy to add several machines with several storages, several disks, and everything. It manages everything. It's fairly it has a fairly good performance, and it's easy to scale together. So if we are doing like scaling the SDR part, you are scaling the worker parts, you should also be able to scale the storage part. So for example, here I have a Ceph node that has 3 machines. So I have 2 servers and one like a small computer that has like 200 gigabytes for testing that's shared among all of the computers. And if you write from one computer or another computer, they all get in the same shares. So I don't have any problems. For example, if one of the workers is writing directly to one of the computers and currently I am accessing the data in another computer, the data is available in any of the machines that's attached to the cluster. So this is one of the things I want to do. I can record, like, for example, if Xquelch is enabled, I can just grab the pieces of the recordings and store in Hadoop block storage and make a small database with metadata and things like that. So it's easy to navigate, find data, and organize stuff. I want also event folder script. So for example, you have a folder called events.d, and then you have the event name, for example, Squelch1, and then you can put like a shell script or a bat script in case of Windows, or a PowerShell script. And every time that event is triggered for that specific worker, it will just run what you want. So for example, if you want to send a message to you saying, okay, the ISS is available, I am receiving signal, you can do that just by making a script and it will call that. Or if you want to trigger something else, like another process, in case, for example, if you have like a trunk radio, that you have a center channel that says which channels are available for calling, then you want to spoil the new channels appears in that list. You just want to get another SegDSP worker to decode that. So you can just put in an event, a custom event saying, okay, when you detect this thing, I just want you to execute this script that will launch another Docker container that will try to demodulate this frequency. Also, another demodulators, AM, SSB, LSB, PSK, FSK. This is pretty trivial. GNU Radio has a lot of stuff. I learned everything I know about DSPs from GNU Radio and a few books that GNU Radio mentions in the source code. So I started with FM because amateur radio in Brazil, it's for VHF and UHF, it's mostly FM. Also, I have the wideband FM signals to test, so it's easier to test. There's not a lot of AM signals or SSB. Especially, I don't have HF antennas right now. And I want a dynamic signal detection. So, for example, like I said, you have an FFT that doesn't have anything there, and you want just to, when something appears that, you want to start recording the IQ for that signal. That's one feature I want for that. Because then, for example, you don't need to know when a weather satellite is coming. You can just set to the weather satellite band and then just say, okay, so when you hear something, just record it. And remote control. So, for example, you have a GQRX that has satellite tracking. Sometimes you want ideally to track the Doppler effect from like the ISS or something, and then you want to readjust the frequency to match exactly the frequency, the corrected frequency. So remote control is ideal. So that's it. It was pretty fast. I didn't have much time to prepare. I'm sorry about that. I hope you like it. If you want to contribute, it's fully open source. I'm trying to decide which license is better, if it's Apache or MIT or GPL. For now, I release it in Apache mode which gives freedom to choose and make whatever you want. I'm still developing that. You can contact me in Keybase, in Telegram, Twitter. Most of the people I know it's from Twitter. And also, this slides will be in my website. That's the last one. There is also the Open Satellite Project backlog when I started making the Open Satellite Project, how was the developing of the Goose, the modulator, and things like that. And do you have any questions? I know probably won't be many, but
we have one question for you.
Okay.
How did the signal bandwidths get detected? I get peak detection, but how does the software decide what bandwidth to channelize down to? How does it do it?
Oh, okay. So basically, for now, it's configuration. So when you start like a SEG DSP worker, you set like the demodulation mode, the bandwidth, and the filter parameters. Depending on the demodulation parameters, you have different. Depending on the modulation type, you have different parameters. For example, FM, you have the de-emphasis. You have like the FM signal bandwidth, the deviation, and things like that. This is currently preset when you start the worker. So basically, you need to know what you're looking for. The idea of the dynamic signal detection is to try to guess what's the best signal. So a peak detector is easy. Detecting what might be the signal might be hardest. But the idea on the end is to get at least IQ recording, measuring in the FFT, like the peak detection, so you know the signal is there's something being transmitted here now, and you can calculate the bandwidth dynamically to see, okay, this signal has like 100 kilohertz, so I probably need to record like 150 or 200 to be safe. Okay, this is not working yet, but it's on the backlog to have a nice way to do that. Like you just say, I want to record and detect the bandwidth of the signal, and then just starts recording the IQ, even if you don't understand what is it.
Okay, let's give our speaker a round of applause. Thank you for sharing that with us.
And thank you for the opportunity to speak here.
Yeah, that's great, and I like it because it actually combines two really interesting things: software-defined radio and DSP, and distributed computing. I mean, that's a really cool way to get into it. I like that a lot. Yeah, that's great. All right, well, thank you very much again for joining us.
Okay.
And yeah, if you've got any other updates, just put them online, and people, we've been tweeting, so people will see that. And good luck with the future steps of the project.
You can ask an ERC or Twitter. So see you, and bye-bye.
All right. Obrigado.
Obrigado.
All right. See you later. Have a good night. Bye.
See ya. Bye.
Okay. Where's my mouse? All right. Next.
awesome high-resolution Earth pictures that you are seeing right here on the right. This picture is coming from GOES 16, that is a L-band geostationary spacecraft. This image is true RGB, the color, with 250 meters per pixel resolution on the red channel. So pretty high resolution images. We started with geostationary satellites because we are not moving, they are not moving, and less gear is needed to receive the signal. So it's better. Just to give you an idea how huge this GRB image is, I will scale this picture on the right here to 100%. And this is Florida with 100% scale. So it's huge. If you want to receive some signal from GOES 16, you might use the lower bandwidth signal, that is the L-band LRIT signal. This is have low bandwidth, so 1 megahertz is perfect for the cheap RTL SDR that you can buy for $21. And you can actually decimate them by 2 to squeeze more, a little bit more SNR. The satellite is just stationary orbit, so you can with them 24/7 without stop. Beyond RTL SDR, we'll need some additional antenna, like this one is a Wi-Fi GSM grid antenna. They are cheap and readily available. I think Alcom sells them on the US. And some form of amplifications like the SPF 5189 LNA that you can buy from China. And if you live in urban area with lots of interference, you would need some low bandpass filter. They are pretty hard to get because they're expensive or not ready to buy. So I made one myself with a fiberglass dual layer FR4 PCB, and is 5th order Butterworth filter made specifically for L-band signals. It is 50 ohm impedance and it's coupled microstrip. So really easy to make. I made this one day, so everyone can do it. I will share the design on my Twitter in a couple of months, just finishing the design. And after your station is running, you can receive images like this one this is the full disk image like you see previously, but sent by the HRIT signal. And they have less resolution, and it is in true color, so a lookup table is needed to make this image colored. But they are still awesome to receive by yourself. Here are more products from GOES 16. This is a mesoscale from the left. Zoomed in, interest data, interest location for the satellite. And from the right, you are seeing a full disk image of another band, that is the infrared band. So the next step for the Open Satellite project are satellites. They are from both X-band and L-band, and the barrier of entry for the X-band is higher than the L-band because the equipment you need is more expensive and harder to get. So we wanted to make that something that can be useful for all users. Since the L-band and X-band signals are more or less compatible with each other, we decided to support both of these bands. So currently, we are almost done with Suomi and NOAA 20 decoder. And this is what I will be presenting to you tonight. We also have plans to support the older NOAA polar orbiting satellites and the Chinese Fengyang. NOAA's older generation is NOAA 19, 18, and 16. So moving up, we have the Suomi and NOAA, formerly known by JPES-1 before launch. They are the latest generation polar orbiting satellites from NASA and NOAA. They have the next generation instruments that improve our understanding of the planet a little more and to predict the weather. They are meant to replace the aging last generation satellites like the NOAA 19, 18, 17, 16, and that are still functioning in orbit after some decades of use. Currently, there are two new generation satellites in orbit, that is the Suomi and the NOAA 20. And the next planned satellites have 3 planned satellites, being JPES 2, 3, and 4, being launched in the coming years or decades. Right? The Suomi and NOAA have, and the follow-up missions will have basically the same instruments. That is the VIRS, Visible Infrared Imaging Radiometer Suite. That is the principal instrument that generate the cool pictures of the Earth. Is the critical instrument of the spacecraft. The other instruments are ozone mapping and sounders to see the surface without even with the presence of clouds, the crosstalk infrared sounder. And HMS, that is the Advanced Technology Microwave Sounder, another sounder on the spacecraft. And all of these instruments send data with the X-band data link. And they will be supported soon by the Open Satellite Project ToolSat. Currently, we are supporting the VIRS that generates the image is most useful for us. The main difference between NOAA 20, Suomi, and geostationary satellites like the GOES 16 are they are moving fast. They are in sun-synchronous orbit, so they are really closer to the Earth than geostationary orbit. So you will need fancier radio gear to receive them. In fact, Dave Newling made made a talk talking about that last Cyber Spectrum, and I recommend you check that out. The signal is the signal sample was provided by Oleg Mitchell at Twitter. Since I don't have a X-band set up by myself, so big thanks to him to make this project possible. Another difference of the GOES 16 to the Suomi satellite is the signal bandwidth that is 30 megahertz. In contrast, you have EdgeReach have just 1 megahertz, so it's huge, the difference. Here in the bottom, you can see the FFT of the signal on the phosphor plugin for GNU Radio. So not all SDRs can receive 30 megahertz of signal at the same time, and even if your SDR supported, your computer, USB controller, or hard drive, or your CPU can be a bottleneck because it's a huge amount of data. So you'll need a current generation computers to handle it well. It wasn't easy to find SDRs that support 30 megahertz of signal, but these have the specs for it. Limes USB can easily support it if your USB controller allow it. As I said, they support 60 megahertz of instantaneous bandwidth. As Blade RF can support it, XGRX, and of course users can support it as well. And I wasn't sure if the Limus DR Mini would work with the signal because the advertised maximum bandwidth was 30 megahertz, 30.72 megahertz, and this is pretty close to the signal bandwidth. And commonly, you need additional bandwidth to prevent aliasing. But I made a test with the Limus DR USB transmitting it here on the top, the Limus DR with the aluminum case, and the Limus DR Mini receiving in the bottom here. And the result was that the Limus DR can indeed receive the Suomi and NOLA 20 signals without a problem. You can see the signal on the top and the QPSK constellation on the bottom here of the GNU radio. The next step is to demodulate the signal. So it is pretty straightforward. It's made by standard QPSK, that is quadrature phase shift keying, with the same IQ power ratio. So nothing new there from the HRIT. So just QPSK is the difference between the bandwidth from GOES and Suomi. And all the GSPs made with GNU radio. That is the hard part of the demodulation is the computation needed because as I said, the bandwidth is huge. So your computer needs to be really fast. And that just recently became available to us, but it's still possible with non-real-time processing. So we'll process, but will take some time. I think my computer takes 20 minutes to process 5 seconds of data. So be prepared to spend some time there. So with some GNU radio blocks that with GPU acceleration, you can accelerate the process, but they're not quite ready yet. These kind of signals are required big boxes with huge and expensive FPGAs to be done in the past. So this is definitely an improvement from the other times. Here it is the GNU radio flow to demodulate the signal. I won't be talking everything here because the time constraint is very tight. So basically you get the signal, you filter it, then synchronize the clock and apply the Costas loops to lock the constellation in place. And after that, you already can see the sync word on the binary view from the file, the output file from the demodulator. And after demodulating, you need to decode the signal that is almost identical to the HRIT signal that have differential decoding, more specifically NRZM, and data randomization to spread the signal energy more evenly as possible to prevent polarization of the channel. Convolutional coding is a method of error correction that is applied here. Exactly the same from the HRIT signal, coming from the CCSDS standard. And the SyncMar is also the same. And we have the last error correction method, Reed-Solomon, that is also present on the HRIT. So it's identical to the HRIT signal. Moving on, after that, we can see more clearly the sync word right there in red, and the fill frames in green. Fill frames are just boilerplate data that to keep the data, the channel data at a given rate. So after that, we get binary data that we can read. So it's from CCSDS. It's pretty standard. So I want to be talking more about it. And after you decode and sort out that frames, the CCSDS frames, you ended up with applications from the instrument. Here I'll talk about the VIRS instrument. So the VIRS instrument is the instrument that produces the images. They have 24 imager channels, AP application IDs ranging from 800 to 823, and they have 5 high-resolution channels with 375 meters per pixel and 17 moderate resolution channels at 750 meters per pixel, so lots of channels. And all channels have the image depth of 15 bits grayscale. Here are the header of the data, so you can see here some channel names, scan count, sensor mode, and others. So it's just metadata of the current line or scan line. Moving on, we have the image body that have the data, that is the 6 aggregation zones here, here, and here. The documentation are not exact on this time here, because there are 2 errors here that identify the segment number that are present on the real spacecraft data. So after you get those 6 aggregation zones, you need to aggregate them out. So it's aligned with 6 of them, and their height are determined by the sensor data. So high resolution have 32 lines, and the moderate resolution have just 16. And the width is made by each channel have their each width. So I can show you here. So it's aligned with 6 aggregation zones aligned. The spacecraft, to prevent sending overlap data, that's duplicate data, they cut some aggregation zone if they identify that the overlap occurred. So from Earth's flat, because the curvature of the Earth, instead of sending overlap data with no value, the instrument programmatically deletes the aggregation zone with overlapping data. So you can see the aggregation zones deleted to reduce the data needed. Then the last step of the decoding of the science data is to apply zones the RICE algorithm that it's like JPEG, but if you take apart some part of the image, they just don't break. So it's patent from NASA. And after that, you need to make some differential encoding on the infrared channels, because since they are pretty close, they decided to just transmit the difference about between them. And see, if you subtract a value from another value that are close, you ended up with a number with a binary number with lots of zeros. So, and the RICE algorithm benefits from long repetitions of numbers. So it will end up using less data. Here is the final image with the image band number 1 with visible light. Notice that no visible bow tie is present here. That is because Lucas made a great bicube interpolation algorithm to hide them, and just them with you just see them with zoom or in dynamics part of the image, like the lower right corner. You have lots of clouds. Here you can see some clouds with ions disturbing the airflow and causing atmospheric waves, and a tropical depression with the bow tie effect in the middle, as well as land data and sea to river deltas. All these tool set will be available at the Open Satellite Project GitHub page later this month. And the bonus part of this talk is the worst SDR ever. I don't have much time to talk about them. It's a boilerplate SDR to you to learn how a SDR really works. So it's made with dirty chip parts from China, based on STM Cortex M3 and M4. That is $1 to $10. They have hardware floating point, building AGC ranging to 7.4 megasamples with 12 bits AGC resolution. That's pretty good. And support SDRAM. That is pretty important if you are going to drive a TFT display with it. They are based open source software based on the OpenCM3 library that supports a wide range of Cortex M4 devices. And I will plan to support the modulation in the future, and from FSK and FM radios, and the tuner can be added like the RTL SDR, the same tuner. You can see the more frequencies, and they are great to learn how SDR works. Here is a FFT calculated inside the SDR, and the left you can see the RTL SDR direct sampling mode, and the right the data coming out from the worst SDR ever. So they are pretty similar. The lower graph, that is FFT, and all this was calculated within the SDR and just display with the computer. Here is the more advanced part. That is a FFT displayed by the ELI9341. That is a cheap TFT screen from China. And the main limitation here is the memory. You can draw the waterfall with the amount of RAM you have inside it. So I will have to buy a SD RAM expansion slot and code that and develop code to use them for the presentation for the FFT. So special thanks to Balint for inviting me, and Lucas Teskey to always helping me, and Oleg to provide the IQ recording that enabled this whole project. So any questions from you? I want listening. I'm not listening. Oh, yeah.
Hi, there we go.
Oh.
How did you design the PCB filter and what software? How did you get the server?
Yeah, I draw it by impedance. I used for a little bit of the designing and impedance coupling. But I will make a easy article at my blog explaining how I made it more with more depth. So I will publish that later this month, I think.
All right, great. Well, thank you for joining us.
Oh, thank you for having me.
You know, the fact that you can see such high bandwidth data from way out there in space, that's one thing. Another, challenging part is you have to do all the format, the images. I found it fascinating that it had this aggregation and pull back together.
Yeah.
It's funny also with SDR, we want things to be better and faster, bigger, go the other way.
Yeah.
Well done. All right.
Thank you.
And catch you later. Bye, guys.
While we're finishing getting all this ready. Thank all of you for actually staying. This is some pretty cool stuff. We want in the village most, so thanks for coming and hanging out. And number two, if you're still here, if you do radio meetup, it's the same thing tomorrow, except social where we all talk to each other about our good stuff. So
Testing 1, 2, 3. Okay, great. All right, so I'll just take it from the top again. So what we created with my platform, Ocean County Radio Live, is a cloud-based SDR-powered P25 and analog trunking scanner, and I'm going to walk everybody through it. We're going to start out with the problem with hardware-based scanners and the lacking that they have with respect to being able to pull in multiple transmissions at once and other issues that they face. So P25 Phase 2 digital scanners are still quite pricey. A lot of people are being left behind due to the pricing, and the RTL SDR really is an amazing platform because for such a small amount of money, you really do get a whole lot of radio. Hardware scanners, they are very limited in the sense that they cannot pull in multiple channels at once. So our platform that we're using 2 different open source software packages to accomplish this. And I'm going to skip over a little bit just because we are pressed for time. These slides are all online. They're on my website. Then they're also at cyberspectrum23.ocradio.live. We made a little subdomain just for this talk. So I go in, the issues with live feeds and scanners, etc. So here is OC Radio Live, our platform. I did a little bit of a play on software as a service. We're calling this a scanner as a service platform. And this is a little bit of an overview of the site and what it does. We're using the open source trunk recorder application written by Luke Burnt, and that's a really great program. It's been implemented for other uses such as live feeds. It'll handle phase 1, phase 2, trunking and conventional, as well as analog and other conventional FM systems. So here in Ocean County, New Jersey, where I am speaking to you from right now, we have an interesting layout of radio systems to scan with this platform. Our county is currently in the process of phasing out their Motorola Type 2 analog trunked radio system. All of the fire and EMS for our entire county currently operate on that. We have a New Jersey State 700 megahertz P25 Phase 2 system that just went online a few years ago, and a lot of stuff is starting to migrate over to that. So you really do need that Phase 2 capability. And then we also have conventional analog VHF and UHF channels. So the magic of SDR comes into play with our platform with the time shifting capability of trunk recorder. On a lot of these bigger trunked systems, what will end up happening is they'll have multiple voice channels, multiple talk groups that can be active at once. And on a traditional hardware-based scanner, you're going to be missing out on that. So we have a distributed network of SDRs that are able to give our users more choices where they can either scan everything and get everything that's coming through our system, or just hear what they want as far as fire, EMS, or any other topics. So this is our first receive site in Toms River, New Jersey. This is pulling in 2 700 P25 systems, as well as some 460 and 155 megahertz conventional channels, and they're all getting fed to the same back end. This is my personal receiving site in my office next door, just a Ubuntu desktop computer, 2 SDRs going into an antenna with a powered USB hub. So here's a look at some of the open source software that's powering the site. The back end, again, is trunk recorder. The radio transmissions are uploaded to an Amazon S3 bucket where they're archived from, and we continue onto the actual backend code. So it's just a simple JSON configuration file. These are all actually up on my GitHub profile as well if you want to see some of our sample configuration files. So you just define the SDRs and then the systems that you want to record in this syntax, and it's really quite simple. You just load it into the program and it will start running as long as the SDRs are suitably connected. And then this is just a little screenshot of some of the console output. If you look at the screen behind me, that's actually the same console output on our production server that's running live behind me. And you can see it just goes, it loads and encodes each transmission, takes it from a WAV to MP3 to save file space, and then it uploads it to our front end server, and then from there to Amazon S3 for the actual archive. So we're at the front end, it's just an Ubuntu VPS, nothing special. We're running the Django web framework, which Trunk Player is a Django app written for. Nginx is a reverse proxy, which feeds it back to Daphne, which actually serves the Django app. So bringing it all together, Trunk Recorder reads in the configuration file. We define the systems we want to record. We allocate them. And then it just executes a bash script when it runs each transmission, sends it to our server, writes it to the database. And then finally, they're stored in Amazon S3 for the archives. And then essentially users can use it to play live transmissions or access the archives, etc. Now, the cool thing is we have a full REST API for all of these radio systems. So we're really trying to see, what people will build on top of the work that we've already done. So with this REST API, you can pull in scan lists, transmissions, all that good stuff. And we're going to end up eventually, probably we're going to build a mobile app, other stuff to go along with it in the future. A lot of that stuff is definitely exciting. And in conclusion, this is an opportunity to bring SDR to a non-technical audience. I've been bringing this to scanner enthusiasts, people that have just listened and didn't necessarily have a technical background in radio. We've been able to use the RTL SDR to bring P25 Phase 2 scanning to individuals that might not have been interested in purchasing a scanner or dealing with the complexity and cost. And overall, I think this is just another exciting application of SDR. And with that, I'll take your questions, and we'll try to do a quick demonstration if time allows us.
Question. Okay, I'll shout into both mics. Hey, there we go. It's definitely working. Hi, Gavin. I'm Zero. Number one, I've been in this room for 13 hours, so thank you so much for... Whoa. That's not going to work. That's a great demo. Oh, it's Bolin. Thank you, buddy. I'm going to step away and yell. So thank you for this. I was looking forward to this one myself, so I appreciate it. Could you contact the Wireless Village team? We really want to be friends. We want to build a system like you've got for the village. Can you hear me at all? No? You lost me? Okay. His audio is dead. Cool. Thank you for muting. I'll pass this back to Bolin.
Okay. I think we're back to it. Yeah, so you've got Zero's request then, right? Gavin, can you hear us?
I can hear you. I have my laptop down here, so you're not coming through my headset because I had to plug into my desktop to get my audio coming through Hangouts. So I can hear you. Your audio's not coming through my headset.
Oh, okay. All right, no worries. So yeah, you heard Zero, right? You heard his request to be friends?
Yeah, absolutely. I'm on Twitter. I'm on my gavinrozzi.com personal site. All my contact info's there. So if anybody wants to follow up on any of the stuff that I talked about, you're always welcome to reach out. Certainly.
Thank you. I'm sorry to end up being a bit of a rush, but I really appreciate that. And taking us through that. It looks like a really slick system. In fact, got the API in nice front end. It's really nice. It's really nice. Good luck with Can you hear me? Hello?
Yes, I can hear you.
Okay. Did you get any of my compliments?
Yes, I did. It was a little bit broken up because we were having some technical issues, but thank you again for the opportunity to present it, and I'm glad you liked it.
All right. Yeah, one last round of applause.
Thank you.
Thanks, Gavin. Catch you next time.
Thank
you.
you.
All right, good night. All right, that brings us to the end of this mega Cyber Spectrum. A big thank you to our hosts tonight at the Wireless Village. Catch you next time. Happy SDRing. Cheerio.